grocery shopping. Right, so you've got all sorts of problems here, and this ends up being sort of like knapsack-like problems, which I'll talk about later, or so you've got some cost, you're making decisions in a market, but here in economics we'd call these posted prices, right? You don't get to go up to the counter at the grocery store and say, no, I only want to pay $2 for this, right? Like they're going to be like, sorry, it's $3.50, do you want the apples or not? So that's sort of one domain. Another shopping on Black Friday. You could actually possibly, like, so much of the sales are online now, you might be able to like actually come up with a software agent. Like this is sort of going about like actually in your store, in a store. You could consider developing a software agent that could actually sort of do grocery shopping, do Black Friday shopping for you if it knew enough about what you wanted, right? Like you have to somehow tell the agent like what you want. Do you want the purple shirt or the blue shirt? Like it has to sort of somehow know enough about you to make a decision like that. Booking flights. So actually there has been some research in my community on these types of problems, where this is more sort of a specific, you have one specific trip, but if you're actually trying to decide not just, you're not just going to buy the tickets today, but you're going to buy the tickets sometime in the next month, and you're trying to actually decide, when's the best time to buy the tickets, because airline prices actually, change cost over time. Yeah, or shopping for classes. This is a little bit of a different thing, and like thinking about Brown total number, all the classes of Brown as a market is maybe a little strange, but it's not that far off. And I thought this was interesting because it really pulls into there's a lot of sort of human needs and wants that are expressed here, right? Like how much you value a class over another one has a lot that goes into it. It's not just exactly what you're going to learn, but the people you'll meet, and like how big is the class or small is the class, what time is the class. Like there's all sorts of things that humans have to think about when they're making decisions like this. So I like thinking about designing agents for these types of problems. But I'm specifically going to talk about my work on ad auctions today. Whenever you're online, you probably see ads, unless you've got a really good ad blocker. And actually, most of these ads are sold via auctions. Auction, right, when I say auction, you probably think like there's someone in a room yelling out numbers really fast and they're selling a piece of art. Or maybe you've seen the TV show where they're selling storage units that people have foreclosed on, right? So that might be what you're thinking of. And this is one type of auction. But there's actually lots of different types of auctions. There's a whole field of auction theory. So I'll explain the sort of necessary auctions when we get to them. But in this space, there's a set of auctions that happen for keywords. So if I search rubber chicken, this is what happens. There's like a whole bunch of ads on this page. I'll go into sort of the parts of that. If I open up New York Times, there's also ads. Here's Merrill Edge, and they've got 3 different ads on this page. Or if even if I go to my Facebook, right? Facebook knows a ton about me, and they've got ads all down the side here, based on. I actually am now doing research on fantasy football, so that's probably why that ad is there. Right. So these are sort of. And these are actually 3 different markets. I'm going to talk about the first 2 because we've done work on that. Actually, the third one, Amy's older student is actually redesigning the auction for Facebook's advertising. He's on the main group that's doing that work at Facebook. So just random things you could do with a PhD. Right. So here's keyword search, which is sort of the oldest type of ad auctions on the internet. So we've got one sort of block of these pictures of rubber chickens, and that's a little bit of a different thing. But the sort of classic view is here. You've got these ads down the side, and we call them like slots. So theoretically, they've done some research that suggests, well, actually the research really suggests that you see like the 3rd ad, but we sort of model it as like being near the top of this list is better. Right? People are going to read from top to bottom, so they're going to see the ad from officeplayground.com rubber chicken first before they see Amazon, before they see these pottery supplies delivered. So the way that this auction happens is these different companies are going to place a bid, and they're going to then rank. Then Google, who's doing the search, running this auction, is going to rank everybody based on their bid. And you're actually going to pay every time someone clicks on the ad, right? So that the advertisers have to pay per click, but you don't pay the price that you bid, right? So maybe the first advertiser bids 3 cents, and the second one bids 2 cents. But the first advertiser is actually going to pay 2 cents per click. So this is what we call a second price auction. And there's first price auctions, which would be you pay what you bid, and then there's second price, which implies that you're paying just enough so that the person who bid below you wouldn't be able to win that item, right? So the person below bid 2 cents, you're going to bid 2.1 cents or something like that, and you're going to pay 2.1 cents so that you're paying just enough to sort of hold your position. So these are called generalized second price auctions or position auctions. So then display ads, if you notice, there's only one company here, right? So we don't have this sort of generalized second price. And also, every time you open up the New York Times, that doesn't mean maybe someone who visits the New York Times, that tells you something about them to a certain extent. But what this market is doing, this is based on ad exchanges. So actually, every time you load the New York Times, an auction happens, in general. And what happens is a bunch of companies will be told by Google, who runs its own ad exchange, there is a person, here is some information about her. She's just loaded the New York Times, and send me a bid and an ad you want to show if you win. So everybody submits their bids and shows and sends their ads in, and then Google is going to run a second price auction. So this is just the highest bidder wins, and they pay the second highest price. So these auctions are happening obviously extremely quickly, right? Yeah, so those are the two domains I'm going to be mostly talking about. So whose problem are the agents solving? Can we think about like this is, I told you about a real world situation, and you know that I'm going to tell you about artificial intelligence and an artificially intelligent agent somehow. But does anyone have any ideas as to sort of what problems I could propose to solve? Right. Yes. Right. How much to bid? So we usually companies like Merrill Edge or Amazon will actually, Amazon probably doesn't do this, but will actually hire another company that's an expert at bidding to do their bidding. So the advertiser comes to this ad agent and says, I want to show ads, I want to target 20-year-old women, and run my ad campaign for me. This is how much money I have. So that's one side of the problem. Yeah. So you don't actually get a lot of information back from these exchanges because it's such a high throughput. They don't have time to send information back. So if you won, and generally sort of over some time frame how much you paid, right? But you don't actually get specific results for every single auction. And you definitely don't know the full set of bids that were placed. So you're working in a sort of information poor environment. But that's a good point. So there's actually a couple of other agents you could think of. So the New York Times, they actually might have a deal with Toyota or something that they're going to show 1,000 ads in the next 2 days of Toyota's ads. And so they're going to be paid directly by the advertiser just to show those ads to people they think are in a certain type. So there's no auction being run there. So the New York Times has to actually decide what it's going to ask the Google exchange to provide an ad for, and what it's going to provide its own ad for, right? So there's a problem there that the New York Times has to solve. So you could think of designing an agent for what we call the publisher, which would be the New York Times in this case. Yeah, there's one more. So there's also the advertiser, right? The advertiser has to pick an ad agent and come up with what the campaign and who the right people to target are, and how many impressions impressions, which are like views of their ad, how many impressions they should show in the next month to make sure that like people are actually coming to their site and maybe buying something. So that's a problem you could think of solving as well. So we mostly work on solving this ad network, this ad agent problem, which is the one that's actually placing the bids in markets. Right, so what about the keyword search problem? Actually, that was the results for. Right, OK, we'll just go. I think we talked about that. So there's a sort of a similar situation for the keyword search auctions, where there's also an ad network that's sort of doing the problem of picking what bids to place. The advertisers have to decide what keywords they're going to place bids on. And then Google itself has to actually decide how it's going to rank ads. So it's a little more complex in reality than just saying like who's the highest price, because they want to get the users to actually click on the ad, because that's the only way they get paid. So if I submitted an ad that was just really awful looking, Google wouldn't want to put it up. So it would want to lower a sort of ad for having low quality. So there's actually a problem there as well. So there are sort of several different problems you could think of in this space. Right. So how do you design an agent for these problems? Right? Like if I told you like this was your job, you show up at actually if you want to work at Google or Yahoo or such as an internship, there's a really good chance you'll be in ads, because that's where they get all of their money. So a lot of people at Google actually work on problems like these on some aspect of this domain. So if I told you like you have to design an agent to bid in one of these auctions, how might you start like even approaching that problem? I don't want a solution. I want like a framework for like how you're going to figure out, is your agent doing well? Like, what's a good strategy? Where might the problems be in your solution? Anyone have ideas? So what if I said, OK, I'm going to design an agent, and I'm just going to start running it tomorrow, right? It's like I've got an agent all programmed up, and I'm going to be like, OK, find some advertisers, and I'm just going to go for it, start bidding in the auction tomorrow. What could possibly happen? Right. I could do very badly. So underbidding would be the good thing, right? Like, OK, my advertisers are mad at me. I haven't fulfilled their campaigns, but I haven't spent tons and tons of money, right? Like, you're spending real money in the real world here. So just deploying strategies without sort of any understanding of what might happen is probably a bad idea. So this is sort of one of the problems that we have in my field is how do we actually, design agents in a way that we're not spending tons of money, but we're still actually coming up with useful solutions. So some thoughts: we could program human experience and intuition into the agent. A lot of agents now actually that are happening in the real world are like this. They have people who have been working as these advertising agents for years, and they just sort of program in basic sort of heuristics that humans have learned. Expert humans have learned. We could model the problem theoretically, write it out in math, and try to solve it. Sometimes that sort of will work. You would have to make a lot of assumptions. But actually, usually these problems end up being, NP-hard problems, or you're making tons of assumptions to the point where maybe a theoretical solution wouldn't actually work too well in the real world. You could build an agent incrementally, right? You could start with something that's like not going to spend a ton of money, that's going to be generally intelligent, and then just sort of improve over time. So now in the real world, a lot of that is happening. They have agents that have been sort of working, and they sort of incrementally make changes and sort of add some theory or add some new ideas into the agent to build the agent slowly. Or you can simulate the problem, right? We could actually write a program that just simulates these markets. So this is actually what my community does mostly. We simulate the problem, and there's, I guess, 4 or 5 games. There's 4 games now, and they're all called the trading agent competitions. So there's the oldest game, which is up here on the left, where you're actually working as a travel agent. Then the next oldest game is Ad Auctions, which are the keyword search auctions. And then they came up with Power TAC. So this is a new. I haven't really worked on this game. I've seen the competitions, but the idea is that you're bidding in power futures markets, and so you're trying to design an agent that can sort of work in that problem well and profit off of these futures markets. And then there's the newest game, which is Ad Exchanges, where you're doing this problem that like when you're loading a New York Times page. So there's these games, and basically what happens is there's usually about 8 agents in this simulated world, and they sort of scale everything down. There's in the ad games, there's only 10,000 users in the world, right? Which is obviously smaller than the true number of people who are using these services. And you're given some data about sort of how the world works, parameters about how often people are searching and how likely are they to search in different types of settings, et cetera. And you're only competing against 7 people, right? Where in reality, we would be competing against hundreds, thousands of people in these auctions, in these markets. And so what happens is, Brown will have an agent. There's a university in Israel that actually created the Ad Exchange game. They'll have an agent. There's agents usually from Michigan, from Texas. So universities are doing research and creating agents that compete in these games. And just so you know, most of the people who have been working on this project for the past several years in Amy's groups have been undergrads and master's students. So if you're interested in research, this is definitely the type of problem you could get involved in. Right, so let's look at like the ad auctions problem a little more. So this is keyword search, right? So we've got these sort of purple dots, which I'm just sort of using as users, right? These are people who are going to place some set of queries, right? Rubber chicken, joke chicken, fake chicken, right? These are things they're typing in. And then the search engine is going to run an auction. And what happens is you've got different advertisers over here who have ads. They've given their ads to 2 different ad networks, right? So these are going to be the competitors, the agents, and they're going to have to place ads place bids into these auctions for each of these ads, what bid to place in the auction, and also what budget to set, right? So you can actually have a little more control usually in these settings where you say, okay, I'm going to bid 3 cents, but after I've spent $200, stop showing my ad, stop placing my bid. It's a little simplified on the number of decisions you can make, but that's sort of how this is working. And usually these ad networks get to place a bid at the beginning of the day, each day, right? So over the course of a couple of months, you're placing a bid. And so the way that Ad Auctions, the game, simulates this is there's actually 60 days, and you place a set of bids for all of your ads each day, right? So you're making the decision, what to bid, what budget to set, but you're doing it, each day. And so ideally I was going to give this lecture after you guys have talked about making multiple decisions, right? So these agents are actually working in a world where, you've been talking about agents who have a problem, they have a state space and an action space, and they're trying to, find some goal state. What's a little different here is that the actions, one, there's stochasticity in the world, right? We don't know exactly what's going to happen. 2, we're actually in a competitive environment, right? There's some other agent out there that's in the world. So this is sort of like if you were, trying to find Budapest, like that one of those, that first example of a graph that we were looking at, but there was some agent that could like close down roads in front of you, right? So you're trying to figure out what's the best plan given that there's this other agent in the world. Or maybe that, there's all the other agents are also trying to find Budapest. And you're going to, you want to find a path that's not going to take you 4 hours because, of all the traffic. So that's sort of another complication. And then there's also this time aspect, right, where you're making a decision today. that not only affects you today, but it affects you tomorrow. And so you're having to think sort of into the future about all of your decisions. But the interesting thing is that usually in these types of problems, yes, each of those sort of complications makes things harder. But usually sort of stepping back and thinking about things from first principles, thinking about states and actions, et cetera. And usually even some of the algorithms that we use to solve these problems are, you've sort of seen them already. Most of my solutions end up looking a lot like heuristic search on hill climbing, in hill climbing type situations. I come up with a heuristic, I have a sort of intelligent hill climbing algorithm, I do intelligent restarts in my algorithm, et cetera. So like that's, it's not always, it's not that far from things you've seen so far. Right, so because we have this complexity of this agent where the agent isn't just, doesn't have a, a predefined set of actions, right? We have a continuous action space, et cetera. And there's all this stochasticity in the world, and we have these other agents that are doing things. We usually think about an agent architecture that looks a bit like this. So we have some environment that the agent is working in, right? So this would be the full game and everyone in the game. And the agent is actually going to make predictions about the world, right? So there's some step where you usually would run, machine learning algorithms or other techniques to predict, what everyone else in the world is going to do, and what's going to happen in the future, and what's going to happen if I make these decisions. So you make all of these predictions, and then usually we move on to a step of optimization where we basically assume that the predictions are correct. Right? That's obviously not true, right? You have some confidence that your predictions are correct and some belief that they're probably very wrong. But generally, like, you can work a little bit of that into the optimization, but not always. So generally, we start at least with, OK, we have the optimization step, and we're going to assume all of our predictions are right. So now we have tons more information than if we just looked at the problem. Right? So I generally assume, like in keyword search, I'm going to actually assume that I know the bids of every other agent in this world. And I know their bids and their budgets, right? That's a big assumption. Like obviously, they haven't made their decision yet. There's no way I could know that. But given past information I've seen and given my knowledge about like, what sort of goals they have, I can come up with a pretty good model, actually. And we have some work that's by a past student who's very accurate, actually, surprisingly, at predicting in this game what everyone else's bids are going to be, or close enough. So I have my predictions, and then I'm going to run some optimization algorithm. This is going to look a lot like hill climbing, like things you've seen. And I'm going to make my decisions. There's going to be some realization in the world, right? We play out the game, and the users come, and they click on ads, or they don't click on ads, and I make money, or I don't make money. And then I'm going to get some subset of observations back, right? Maybe I don't get to see everything, but I get to get some information back about what happened in the world. So this agent architecture is sort of where we're generally starting from. So thinking about the keyword search auction, the optimization problem is generally, there's a little bit more to it, but I've tried to sort of scale it down so that we can maybe talk about it a bit more. So given all other agent bids for all keywords and beliefs about the set of potential users, right? So I have a belief about like who's going to show up and click on ads and what they're going to do. Decide what to bid and what budget to set for each keyword in the next 60 days. Right? That's sort of the problem that I'm working from. Does this sound like something that like you could start to tackle from what you know? No isn't the acceptable answer, but I was hoping that it would sound like not completely impossible, right? Like if someone gave you this task at your internship, you might know where to start, given especially like the rest after you see the rest of this class, you'll know where to start. So I want to talk a little about like get feedback from you. How do you think you might model this problem? Like this is sort of an abstract real world thing that's happening, but in computer science we generally try to come up with some sort of model. I usually think I think in pictures, and then I translate it into math. So does anyone have any ideas about like how they're thinking about this? Anybody? No. OK. So this is our representation of the problem. Does this look strange? We call this the waterfall. I have a new problem, and I think it's also a waterfall, which makes me kind of happy and kind of like, woo, not again, no more waterfalls. So what happens here, what all this is we have our slots for our ads, right? So this would be, the top ad that's shown is in 1, all the way down. And then maybe there's someone hanging out here who has bid, but there's not enough slots for them. There's only 4 slots in this world, and they're the 5th highest bidder. So we have what they bid, which you can see is, decreasing. And then what this represents is time. So this axis is time, right? And what happens is there's users coming and clicking on ads. So you're getting impressions all the way along in this time. And if you see that this green person, right, they bid 0.03, they bid 3 cents. The person below them bid 2 cents. So they're paying 2 cents. But at some point, they get enough clicks that they've hit their budget, right? So they disappear. Green's no longer there. And what happens in this auction is that suddenly they're not bidding anymore. So the person who was originally in slot 2 is now in slot 1, right? So everyone's shifted up one slot. And this person down here who had bid 0.004 cents, or yeah, $0.004, will now suddenly pop up into the auction. And they're paying some price of someone below them. And then, we're going along, and the purple agent drops out, right? And so everybody shifts up again. But the red agent's still there, so they don't shift up to there. Right? But this is sort of what's happening throughout the day, right? People are hitting their budgets and dropping out of the auction. And obviously, they're getting some different number of impressions. They're paying some different amount. They're getting some number of people who are visiting their site and maybe buying things, right? So they're getting some reward for showing these impressions. But this is generally like how we're thinking about the problem. So, let's think about if we're the purple agent. Like we placed the bid for 1 cent, and this is what happened. So if I knew all the other prices and budgets of everybody else, if I said, OK, well, I'm going to bid 1 cent, I could draw this waterfall, right? It's sort of a weird algorithm to think about how you would actually draw the waterfall, but you could actually come up with OK, what happens all the way along the game, because I've made all of these predictions. So then I'm like, OK, well, maybe, what if I bid 4 cents, right? I want to be on the top of this auction. And then this might happen, right? So I have all the data about all of my other competitors, and I can draw out this waterfall. And it looks a little different, right? Everybody else's results have changed as well. But I get some different set of piece of this waterfall, right? There's all these users out there, and we're competing for them, but we're going to get them at different times, at different prices, et cetera. So once we've modeled the problem this way, we can actually take out those decisions, right? So my decisions are now, I'm going to bid to be in the 1st slot. I'm going to bid to be in the 2nd slot, 3rd slot, 4th slot, right? And this is sort of an abstraction, right? But you can see that these might be the chunks. And for any given chunk, I can tell you, how much I paid for it, how many impressions I saw, which is sort of the information I need to know to know how good of a decision that is. So I sort of take all of my predictions and I say, OK, if I've been in the 1st slot through 4th slot, tell me what's going to happen. I could do that also for a different keyword, right? So rubber chicken versus joke chicken. I have different predictions about what's going to happen, and I can see, OK, here's all my predictions about what's going to happen in the world. And then I've got these sort of other values here. So in ad auctions, the game, there's actually a constraint where if you only have so much supply in your warehouse, right? So if you have too many people who come to your website and click and buy something, then you're actually going to have to start telling them, I'm sorry, we don't have that product. I'm sorry, we don't have that product, which is really damaging to a company, right, if they have to do that. So to a certain extent, they have to actually modulate, how much they're selling, how good of an advertising campaign they're having. Because it's really bad to show up and say, oh, well, actually, glad you're interested, but you're going to have to wait 2 months for that product. So I can predict, though, OK, I'm going to have $300 worth of revenue, and I will have, from 30 people. I saw 30 people. Or I can have 200 from 25, 150 from 20 people, etc. So that's sort of what these values are. And the interesting thing is we've gone through all this, like this doesn't really look like the problem I told you about, right? Like I've got these shapes and these values and these sort of constraint where I can only have a certain number, right, of impressions in a day. So I can't choose to have 30 people buy my item there and 20 here because my warehouse only holds 40, let's say, right? So then I've gone over my total number of sort of items I can sell. So that's one constraint. Also, like, can I choose to bid in the first and second slot of an auction? No, I'm seeing heads shaking no. Right. So like Google isn't going to let me place my bid twice, right? If I'm the same advertiser. Plus, it wouldn't really have any value to show my ad and then show my ad again, right? That's not in my model of how this is working. So I've got two constraints here. We haven't really talked much about constraints so far, but you can sort of think about that. Like this really does show up in the human world. I deal with constraints a lot, right? Like I can only pick one from this column, and I can only pick one from this column, and the sum of the number of items I sell has to be less than 40, right? So I'm dealing with two constraints here. The interesting thing is, if you know some algorithms, or maybe if you've been introduced to the knapsack problem, this is actually the multiple choice knapsack problem, which is a variant of the knapsack problem where I have this sort of extra constraint where I have to pick, one from this column, one from this column, and maybe, there's a whole other set of terms I could be considering, right? There's a whole other set of auctions I have to make decisions in. So we've done all this obscure modeling and worked out this problem, but that was the hard part to a certain extent because we get down to the multiple choice knapsack problem, which has a greedy algorithm, which is actually a two approximation of the solution for this problem, which isn't great, but in practice, it actually works very well, this greedy algorithm. And then my most recent work is actually on a heuristic search algorithm that in practice does even better than that. So we did all this sort of obscure work, but it ended up being this basic problem that you probably actually will encounter in your years of undergrad, right? So that's generally how these games and how this sort of approach is going to work out. If you do the right modeling, your solution becomes easy, which is a little different maybe, I think, than sometimes we think about. Like, oh, like modeling the problem, that's not hard. Like learning the algorithm to solve it, that's the hard thing. But thankfully, there's a lot of theorists who solve our problems for us, generally. So I'm going to go on and talk about the other game. So this is the newest game on ad exchanges. And right, so this is going to look a little bit similar, but there'll be some differences. And we're going to come up with a different modeling solution in the end. So we've got users over here. But now we actually care about the type of person, right? So there's the orange person and the red person and the purple person. And they're going to visit some set of sites. So they're visiting New York Times or Fox News or Yahoo. And they're seeing ads, right? So here's an ad. There's an ad for some fashion website. And then there's that same sort of Merrill Edge ad, I guess. And so each of these different publishers is going to say, OK, I have a user. They're going to tell the ad exchange at different points, or basically simultaneously. I have this user. They're on this site. Send me an ad. And then there's these group of advertisers, and they have picked an ad network to work for them. And the ad network is going to get this request from the publisher, get this request from the exchange for a given publisher, and return an ad, right? An ad and a bid. OK, so this is sort of the real-world complex problem, but let's just think again about this optimization problem. Let's assume that I've made predictions about the world and how it's working. And I can say, OK, well, given information about a user, right? I know information about what type they are. They're a young female. They're on the New York Times, et cetera. The makeup of the set of all users. I know who I'm going to see that day to a certain extent. I know that there's going to be 300 women and 300 men, and there's going to be, you know, and half of those are going to be older, and half of those are going to be younger, et cetera. I know the makeup of the user set. And I'm going to also assume that I know what all the other agents in the world are going to bid, right? That's a big assumption. And I'm going to assume that I know what campaigns I have, right? So I'm an ad network. I'm working for a set of advertisers, and I know all the information about, you know, what they want, what they're going to give me. So this is the math. Don't actually need to know anything about this math. I'm just showing you that, like, this is actually part of the step as well, right? Like, I have this sort of pretty in-words example, but in the real world, like, we end up writing something that looks a bit like this. I just finished this morning. It was very exciting. And right, so how are we going to model this problem? Does anyone see anything? What does this look like? A bit. It's a data structure you've probably seen a lot. What? A graph, right? We've kind of got like things that are going into other things. You could think that, like, okay, there's sort of numbers of things in here, and we've got decisions we're making, and et cetera. And okay, so that's how we're going to look at this. Right, we have users, and they have types. And right, so all the green users could be sort of categorized as one type. And we could think about decisions we're going to make for that type. And then at each of these types, we're going to be running an auction. We can sort of say, OK, well, all auctions for young females are going to look basically the same, right? Everyone else has the same information about them, basically, and we're going to have one type of auction, one sort of setting I could end up being in, and I'm going to predict what everyone else will bid for young females. So I'm going to actually have some cost curve. I can, from that information, if I'm like, OK, I know what everyone else is going to bid, I can know that if I want 100 ads, you know, if I want to show 100 ads versus 150 ads, I know what my cost will be, right? There's some cost value here. So I have one of these for each type of person. And then I know my campaigns, right? So this is the Stitch Fix and the online game and whatever the Merrill Edge advertisers. You know, they've given me a campaign, and they have a revenue curve that I can also either work out or they've given me, where, you know, okay, this is my revenue if I send them 1,000 people, right? If I show it their ad 1,000 times, this is my revenue if I show them 1,500. Their ad 1,500 times. So I have that information, and then I'm going to say, OK, well, these users, I can sort of aggregate them all into their types, and then I'm going to send people of different types to different ads based on maybe like what the campaign is looking for, right? So let's say that the video game advertiser only wants to show their ad to young people, right? They don't really have value for someone who's 70 years old, right? And the Merrill Edge ad doesn't want to show it to 6-year-olds, right? Like, there's no way the 6-year-old is going to click on that. Hopefully, the 6-year-old's not searching online alone, but whatever. Or on the New York Times. Right. So I have some, you know, I'm going to decide, OK, I've got 300 users here, and I'm going to send some number of them I'm going to show some number of them this video game ad. I'm going to show some number of them, right, this fashion ad. Which means that my decision here is I have to pick a certain number of users of each type to show to each campaign. And when I do that, I can tell you how much it's going to cost me, right? Because I know, you know, I've got total number of users of this type. I can tell you, because based on my cost curve, exactly how much it's going to cost me. And I'm going to tell you by summing up, you know, the revenue that I get from these for this campaign and the revenue I get for these for this campaign. And actually, the confusing part is all of the other combinations, right? I have to care about the revenue here is not just a function of what I decide here. It's also a function of what I decide for the red type users. But I can sort of work all this out, and there's math that can work all this out. And so I know my revenue, right? And then basic economics, we're trying to maximize our profit, right? Revenue minus cost. So I've now taken that sort of obscure game, and I've modeled it as this problem that looks a bit like a flow problem, which some of you may have seen, some of you may have not. But I have a graph, things are connected, there's sort of a direction that users are flowing, and I want to make decisions about how they're going to flow in this graph so that I'm happiest. So this is sort of at the point where our research is right now. We have this graph, we have this ugly math I showed you, and we're now deciding what algorithm we're going to use to solve this problem. With a little more tweaking, we think we can actually get it to a weighted bipartite matching problem, which would be great, because there's several algorithms that solve that for us. But we also sort of have another hill climbing-like algorithm, where you actually just are going to make one change. You're going to add one user to this graph. So I would say, OK, this is my current state, right? And then my action is I can either add one here, or add one here, or add one on each link. And I'm going to go in the direction that increases my profit the most, right? So that would be a sort of algorithm we think actually would produce a good solution to this problem. Right, so again, right, we did all of this work to somehow squish this problem into this problem representation, this model of this problem. And then we have a solution. Or, not quite a solution yet, but we know where to go with the problem. And we can pretty easily, code up, think about theoretically different algorithms, and decide which one's going to be the best. So what are the benefits or drawbacks you could see in using simulations like this, like the TAC Ad X game, to actually solve this real-world problem? So if I took the agent that I designed for TAC Ad Exchanges and actually tried to maybe make some minor edits so that it could work software-wise with the real-world ad exchange, what's going to happen? What might happen? Right. So I've got scaling problems. I'm only dealing with 8 competitors. I'm only dealing with 10,000 users searching.
If everyone's doing it, it might change the problem itself.
If everyone's doing what?
If everyone's making a similar AI to solve the problem, then the problem statements look different as far as what other people are doing.
Right. So I made all these predictions, right, about what other agents were going to do. And I made decisions about how they were going to bid in the auction. And there's actually this problem gets a little more complex in that, it's actually happening over multiple days. And I'm actually have 2 other decisions I have to make on top of this, right? I have to actually decide what campaigns I'm going to compete for, right? There's multiple ad networks out there, and I have to compete against them to get my campaigns. So I have to decide how much I'm going to tell them I will charge them for their campaign. This is a reverse auction. And then actually, I have to actually go to another service that's going to give me the information about the user. The ad exchange doesn't actually tell me all the information about the user. There's actually other companies. There's a company like Turn that's a startup that I know some undergrads have worked at, et cetera. And they actually do all of this data mining on they're tracking behavior online, so they're the ones who actually have the data, like this is, a 20-something-year-old female of low income who's living in Rhode Island, and et cetera, right? They actually gather that, they know that I go to fantasy football, they know that I read the New York Times, et cetera. They know that sort of information about me, but I have to pay for that information, right? And there's different levels. These companies provide different service, right? So some of them know a lot, some of them know less, and obviously if you know a lot, you probably have to pay more for it. So I'm making those decisions on top of this as well, right? Which isn't in this problem, it is actually in the game. But once you make all of those decisions, right, assuming that you've gotten it correct is probably a bad assumption. And right, there's a lot of game theory in these problems, where if I start doing something, then it's going to change someone else's behavior. Once they change their behavior, then I want to change my behavior. And you hope that eventually we're going to find an equilibrium, right? We sort of do this changing enough, and we all sort of decide that, like, actually this is the best. And like, given what I'm doing and what everyone else is doing, I don't want to change, you know, my behavior. So, right, well, let's, so some benefits, right? We don't have the monetary risk. It's theoretically tractable. And we actually have a metric to compare solutions, right? It's kind of hard in the real world to know, like, oh, well, you know, I did this well this month, and I did, you know, I used a different algorithm last month, but like, what else has changed about the world in that month, right? It's really hard to actually compare different solutions in the real world. You can do A/B testing, which, like, obviously a lot of people will do, right? So at the same time, you're running 2 different algorithms. But that could be kind of risky. And then also you're affecting yourself, right? Because your strategy is then playing against your strategy, and like that gets kind of complicated. Right, so we talked about scalability. We talked about the problem being a little bit about being too well defined, right? We know a little bit too much about exactly how the world works. Whereas in reality, we're sort of making predictions about these things as well. And once you start adding in all of this stochasticity, it becomes harder to sort of know that you've got the right prediction. And we're not always given a clear objective function in the real world, right? Like, the people who are making decisions about what a good solution and a bad solution are generally people, you know, high up in a business who are happy or upset with the way that things are going, right? It's not exactly as easy as, like, here is a function, and if you find a really big value, you know, if you optimize this function, then I'm going to be happy. It's not quite that way. And then there's also a common problem in our field that a lot of us are trying to work on, is overfitting to the game. Right? You can come up with an algorithm that works very well in the game given the certain parameters, but people have actually done research on these games and shown, well, if you tweak this parameter even by this much, all of these agents who win in the game start losing, right? Because they're all tuned to these parameters, and they're all overfit sometimes to these parameters. So this has actually, like, I've been working on these games, and it sort of motivated my next research, in that I'm trying to actually sort of step back and think about how does an agent really learn what the person wants? And how do we deal with the fact that, right, I've got an agent who's making decisions, and I'm modeling other sort of rational agents. Like, that's sort of what I can do, is I can model, like, if I was another agent, this is what I would do rationally, and then this is what would happen in the game. But in reality, I'm playing against other agents. I'm playing against irrational humans who have sort of different objective functions. So that's sort of the direction that my work is going. So that's technically what I have. But I would love to answer questions or talk more about other problems. Or if you're interested in learning a bit more about, you know, sort of more of the details of the games, of like what the other sort of real problems we're trying to solve are. Or if you have questions about the class so far. Yes, me? Right, so what happened with both of the games, so for Ad Auctions, actually people went and talked to what was Yahoo Research at the time, which is now Microsoft Research in New York, which is not the one that's shut down. So they actually went and talked with them and modeled the game based on how they designed their keyword search auctions. And then with Ad Exchanges, the same process was done with Google. So they went and actually met with people who were working on Google, and I think some Yahoos as well. So usually what happens is someone in the community finds an interesting problem and then spends some time talking to people who actually run these exchanges in the real world, because they're even more complex than the games in the real world. And they try to figure out what's really important, where are the problems. So one problem that was sort of the ad exchanges, there was a big toss-up as to whether we were going to try to solve the ad networks problem, right, like bidding in the auction, or whether we were actually going to try to solve the publisher's problem. Because no one's really working on that problem, right? This is the problem where we're trying to decide, okay, a user comes, am I going to show them an ad that effectively I've already been paid for, or am I going to put their ad into the exchange? So no one's really trying to solve that problem yet, but so there was a big toss-up as to which problem we were going to solve. No. Yeah.
I have a question about the ad exchange. So,
Uh-huh.
we model that with the graph, but you mentioned on the slide that we can solve that by party matching. So I'm kind of curious how to do that by party matching.
Yeah,
It's not linear.
Right, no, it's right, because the cost functions aren't linear, and the revenue function isn't linear, and like, what do you do there? So actually, it's by some fancy discretization is our plan. So basically, what you're going to do is you're going to create you're going to create a node for you're going to take a couple of samples in this cost function, and you're going to create one node for each cost, right? And so you're then going to effectively say, like, okay, you can only choose one of those, like, yeah, so you can actually sample, like, okay, I can have this many at this cost, or this many at this cost.
But the price of ads actually change if I show more ads.
Right, the revenue is going to change, or the price is going to, oh, okay.
Both of them change. So
Yeah. This is a trick that someone else in my group actually came up with, which I've been told works. I have yet to completely validate it. I'm hopeful, because it would be nice if it was just a solved problem. Yeah, so we tend to do sort of some discretization work of trying to not get into all of the details. Right, so instead of this edge being the number of users, it's actually going to be some value that you want to accept, some revenue minus price. Why is it going to sleep on me? Does anyone else have the bug with the MacBook Air where it like the new ones where they like go black, the screen goes black for a while and just like doesn't want to wake up? No. Okay. That means it. Anyway, so right, so oh there it is. Yay. So instead of this being the number of impressions, we're actually going to do the calculation, right? You could actually just say, okay, for each node, I can connect it, and I'm just going to say, okay, I'm going to sample. What if I had 100 impressions coming out of this node? What would the cost and the revenue be? And then actually turn this into the true value, right? So then you're actually doing a weighted matching because you're picking the value that you want on each edge, as opposed to picking as opposed to actually picking the decision you're making. And then you convert the value that you want back to the decision, right? If you have functions that can create the value, then you can sort of take that information and roll it back into what the decision would have been. So I think that that's the direction you're going, where you're not actually getting to solve like with the complete discretization of like choose one or choose the other. You're sort of sampling from possible realizations of this and picking what's the best decision, what's the best result, and then backing that out to what decision you have to make to get that result. Yeah?
How much time do each of these agents have to make a bid, and like what sort of infrastructure is in place so that this all happens like instantaneously?
In the real world or in the game? In the okay, in the game. Right. So you have on the order of, I don't know, it's milliseconds. It's yeah. And the infrastructure, they have it down to where they're sending a little amount of information as possible. This is why they don't give you information back, right? The exchange doesn't give you information back. But a lot of the details of the infrastructure are sort of trade secrets to a certain extent, right? Having a really good fast exchange means that you're loading pages faster, et cetera, which is a definite advantage. And I'm not a systems person. From what I get, it's very hard. Like, there's extreme limits on what information you can pass back and forth. There's actually sort of a danger if your agent isn't fast enough. If you stop reporting ads, like you tell the exchange at different points, like, hello, I'm here, send me ads. And if you don't respond with ads, the exchange will stop sending you like a notification that there's an ad going on. Right, because it's in the exchange's interest to only communicate with like working, smart agents. So that's sort of a concern as well, is you have to, sometimes actually you have to place really low bids that you don't actually want to win just so that you're staying, in the real world, you have to do that so that the exchange still knows like you're there and you're placing, you want to keep placing bids. But yeah, no, so there's definitely a lot of systems work that goes into building these exchanges. Yes?
Why is the second price auction the chosen auction?
It's a great question. Okay, so that's a bit of auction theory. So second price auctions, let's just think about it, like do a thought experiment. So I'm going to tell you like there's going to be 2 people in the auction, or 3 people in the auction, and if I'm running a first price auction, right, which means you're going to have to pay what you bid. And we all have different values for the item. Let's say we're auctioning off, I don't know, tickets to a concert. We all have different values for it. So if you knew what everyone else was going to bid, you could bid just above, right, the second highest bidder, and that would be a smart decision, right? You would pay what you bid, but you wouldn't be overpaying. But think about how unhappy you would be if you bid, let's say you actually have a true value of like $100 for going to this concert. So if you bid $100, then, and the next person only bids $75, you've paid $25 more than you needed to, or $24 more than you needed to, right, to win this item. So the way that the theory works out is, if I tell you that it's a second price auction, you can then just tell me what your true value is, right? That's a hard part for humans to really do, which a lot of people gloss over, right? Is figuring out what their true value is. But if I say, okay, just send me your true values. If everybody sends in their true values, then someone's going to send in 100, somebody's going to send in 75, someone's going to send in 65, and then you'll get the item. But your decision is easier, right? So it's just from like a game theory, auction theory point of view, your decision is easier in a second price auction, because you just have to tell me your true value for winning. Whereas in the first price auction, there is a way, you have to have a prediction about what everyone else's bids are going to be. You have to have that information before you can make a smart decision, because you don't want to bid your true value. You would have to like predict what everyone else is going to be, and like, if you have a good prediction, maybe it's okay. But there's still, more computation that you have to do there. So second price auctions. And if you think about the auctions you'd see in a movie, right, where it's like, oh, $2, $2, who says me $2, $3, $3, that's an ascending price auction. But it actually ends up being equivalent, right? So if the last person bid $5 and then you bid $6 and no one outbids you, right? Maybe your true value is $70, but you got it for the second price because I was willing to bid 6, but I wasn't willing to bid 8, right? And so it actually ended up being, it's what we call revenue equivalent. It's equivalent auction. Any other questions? So if any of you are also econ majors, or just like econ or problems like this, we're actually just now creating agents for the ad exchange. So if you get in fast, you could still maybe participate with us on this ad exchange agent. I'm going to let you go unless other people have questions. You can also stay if you want, or if you're ready to go, you can go as well. Thank you guys for coming and listening. And Stephanie will be back on Tuesday. Oh, thank you.